I think we can start now. So, are the slides visible? Okay, so we have some questions from the last class that we had not done yet related to vacancies and the like number of vacancies and related energy formation. First, we'll try to do one of the numerical on that. It says that in iridium, the vacancy fraction is given by 3.091. 10 to the power minus 5 at 1234 degrees Celsius, and then we have another concentration of vacancies given at a melting point. So you have to calculate the enthalpy of vacancy formation, which is delta HV. So you have to find, we are given the melting point of iridium. So based on your relation, that gives you an idea about the number of vacancy formation and the variation of the number of vacancy formation with respect to temperature, which says that if you have a relationship like this, which is exponentially related to your factors like Q, right? So you are given a vacancy fraction. So you are given actually the value of your N by this capital N, which is equal to e to the power of minus Q by RT. Okay. So you are given at two temperatures. So you can take one as T1 and another as T2. Say for example, this is N1 and this is T1, and then you will be also having for N2. So that would be N2. So you have two equations which are given here with two different temperatures and two different vacancy fractions. So you can divide the two equations and then you can find the value of your Q which is required, which is actually the same as enthalpy of vacancy formation, right? The energy to form a vacancy. So you can try to solve this equation. You can take 1 minute to solve it and then you can tell what is the answer that you have arrived. So for starting, say for example, we can write so you have to find the value of your minus Q by R. Actually minus Q. R is the gas constant. So you can tell me the value of your Q. You have to change the value of your temperatures to Kelvin. So this is 1234 degrees Celsius. You have to, this is your Q1 for a like for first T1. So you have to change it to Kelvin. 1234 plus 273. And also for your melting temperature, which can be taken as T2. So that is 244 plus 273 degrees Celsius.
That is the answer, 144 kilojoules.
Uh, the answer is yes, 144 kilojoules, right? It is actually kilojoules per mole, right? So this is your answer. You can take a 1 minute for solving all of you, and then we can move to next question. Should we move to the next question?
Yes, ma'am.
Okay. So we have another question that says that this is related to your phase diagrams and formation of your lever rule, how you calculate the phase fractions. So this is a diagram for phase diagram where we have two compositions. We have copper, we have silver. So you are adding silver in the copper and then forming a copper silver alloy. So this is a diagram, and you are given that you are for a copper silver alloy of composition 25 weight percentage silver and 75 percentage copper. So that means we are somewhere here. This is your 25 percentage copper, somewhere silver. So we are somewhere here. So and you are given a temperature of 775 degrees Celsius. So this is 779. So we are just below this line, right? Below 779. So you have to determine the mass fraction of alpha and beta. So actually in this diagram you can also see that you have a liquid that is forming a eutectic point, and then that liquid is getting converted to alpha plus beta to two solids. So you have a eutectic point at 71 percentage and temperature of 779 degrees Celsius. You are asked to calculate the mass fractions of two phases below your eutectic temperature, right? It is lower than your 775 degrees Celsius. That means your liquid has transformed from this state to pass through the eutectic region, and then it has converted to the two solids alpha plus beta. So you are actually in this region alpha plus beta. So you have to calculate the mass fractions. You have to calculate the mass fraction of primary alpha and eutectic microconstituents. Primary alpha is nothing, it is actually the pro-eutectic composition, because we are not exactly at the eutectic. If you are exactly at the eutectic, you will have liquid getting transformed into alpha and beta. But if you are below the eutectic point, then you are in the region of hypoeutectic region, and if you are above the eutectic region, you are in the hypereutectic region. So below your hypoeutectic, there is a always a constituent of primary alpha, which is uh, for solidified along with your eutectic mixture. So you have primary alpha and eutectic mixture, while as above eutectic point you have primary beta and eutectic mixture solidifying from your liquid melt. So you have to calculate the primary alpha and eutectic microconstituents, and you also have to determine the mass fraction of eutectic alpha. So you know that your first thing that you need to know, you have to know that we are below the eutectic temperature. So we are less than the eutectic temperature, right? Point two is that we have constituents of uh, two things. One is the eutectic mixture and another is primary alpha. So we have eutectic mixture and primary alpha, but this eutectic mixture also consists of two things, which is alpha and beta. So you have two alphas, right? One is the eutectic alpha, and one alpha we will be denoting by primary alpha, which is alpha p, say for example. So you have to in this question actually calculate this primary alpha, and then you have to calculate what is the eutectic alpha, which is this alpha. Okay, so now we'll try to solve this. Now you have to see it is around this temperature. It is lower than 779 degrees Celsius, somewhere here, right? So you are at a 25 degree, sorry, 25 percentage composition. So you are here. So if you draw a lever based on the lever rule, so your desired concentration is 25. Since we are in the alpha plus beta region, your final region is this 91.2. I'm sorry for the handwriting. So this is 25, this is 91.2, and then you have to see what is this. This is your Solvus line. You take this composition as 8, okay? This is 8 weight percentage, because this is 10 less than 10, so you can take this as 8 weight percentage. So this is 8 weight percentage, okay? Now you can find the mass fraction of alpha and beta based on this lever rule. So how this fraction will give you alpha and this fraction will give you beta utilizing this value. So if you have alpha, you will have alpha equal to 91.2 minus 25, and overall composition of the lever, that is 91.2 minus 8. So this is your alpha. What is the alpha? If you calculate, what is the weight fraction of your alpha? You can write this as to be as weight fraction of alpha. So what is the value of alpha? Can anybody calculate? So you have to calculate the weight fraction of alpha. Have you calculated it? You're not audible. Anybody? What is the value of your mass fraction of alpha? We are trying to solve the part A of the question. I think the value is around 0.79, which is 79%. So we have weight percentage of alpha as 79%, right? So what will be the weight fraction of our beta? Anybody? Because our mixture consists of a mixture of our mixture is having two phases, alpha plus beta. So what will be beta? So it will be 1 minus the weight fraction of your alpha, right? So our weight fraction of beta will be 0.21. Is it clear? Is it clear so that we can move to the next part? We have to do this question of part B. So now we'll do part B. The part B says that you have to determine the mass fraction of primary alpha and eutectic microconstituents. So for primary alpha, because we are in this region of 25%, we have to calculate the primary alpha. If you closely see the diagram, it is actually the liquid from this region. It has transformed to alpha plus liquid. That means all the primary alpha that was to be transformed has transformed in this region, and then we are only left with the liquid, and that liquid then will be transformed into our eutectic mixture, right? So in order to calculate this primary alpha, we should use this region which is around A, B, E. So in this region, we can calculate our primary alpha or your eutectic alpha to determine our part B. So for part B, if we are around this region, so we are around 25 percent of say for example above, we take a region above this eutectic point at 25 percentage alloy composition, so we will be somewhere in this region, right? That will give us our primary alpha, right? So because we do not know the exact end point, so we will choose this eutectic point as our region for determining the alpha. So for that we will have again a lever and now our central point is 25, right? Our end point for this eutectic line, which is ABE line, so we have the end point as 71.9, and we have our initial point here, which is B, that is as 8. Now you can calculate the weight fraction of your pro-eutectic alpha or primary alpha using this. That will be equal to 71.9 minus 25 divided by the complete lever, which is 71.9 minus 8. So that will give you the weight fraction of your alpha. So that is your primary alpha. So primary alpha will be equal to 0.73. Right? So you have determined the mass fraction of primary alpha now. Now you have to determine the eutectic microconstituents. So because you know this liquid, we have two phases here, alpha and liquid. Alpha is the primary alpha, and liquid will transform in the form of eutectic mixture. So whatever phase fraction you get for the liquid will be transformed into the eutectic mixture of alpha plus beta. Okay, so you have to calculate for the eutectic mixture. Okay, so for the eutectic mixture we have this liquid. For that we simply will have the weight fraction of this liquid, or we can say the weight fraction of the eutectic mixture, that will be equal to 1 minus this 0.73. Okay, that will be your weight fraction of the eutectic mixture, and that will be 0.26. Okay, now I want you to do the last part, which is the part C, and tell me what would be the answer. So you're asked in this to determine the mass fraction of eutectic alpha, right? You are only this is the weight fraction of complete eutectic, not only alpha. So it consists of both alpha and beta. This is a mixture, eutectic mixture, while you have calculated for the primary alpha. Now I want you to determine what is the mass fraction of eutectic alpha only, not the complete alpha of transformation, but only the eutectic alpha. So you tell me how we can do the part C and what will be the answer for that. You can take 1 minute and then you can answer. So anybody can attempt this question, the part C. You can try to attempt it, even if it is wrong, we can try to solve it later. So we have anybody with the answer?
Will it be 0.06?
You're not audible, I think. Can you be a little loud?
Madam, will it be 0.06?
I think you're saying it is 0.06, something like that, right?
Yes, ma'am.
Okay, so how we try to solve it?
Ma'am, we have total mass fraction of alpha from part 1 as 0.79.
Yes.
I subtract 0.73, which we got in the part B.
Right. So we are actually, you understand that you have alpha coming from two regions, which is from the eutectic mixture and one coming from your primary alpha, right? So you are asked to calculate only this eutectic mixture. So what you do, you take the total alpha. This total alpha will is already given from your part A because you have determined mass fractions of alpha and beta phases, and then you have to subtract it from the alpha that you calculated in your part B, which was for the mass fraction of primary alpha, which was this 0.73, right? So you have primary alpha, I will write this as alpha P. So you have to subtract 0.79 from minus this 0.73, right? So that was your total alpha. That is your, sorry, eutectic alpha, and that will be 0.062, something like that, okay? So this is your how you have to approach for this these type of problems where you have to distinguish between your primary alpha, eutectic alpha, and whether you are in a hypoeutectic region or in a hypereutectic region. So based on that, you will have a transformation of your phases from liquid melt to different phases, binary phases. Okay. So
Ma'am, would you highlight the solver's line of this diagram? Will it be only BC or it will extend up to P point, solver's line?
the solvents line is this BC.
Only
Actually,
BC.
yes, actually the solubility is too low after that, and you will see there is no particular trend after this diagram drawn in most of the cases, even for your Ferrari diagrams. So this is only a solubility, it reaches a solubility limit. It starts from some point and then reaches B. It is never zero. So there is always some difference for the solvus line. So it is B to C.
Ma'am, how would you define the solver's line? We have defined liquidus line, we have defined solidus line. What is the definition of solver's line?
Solver's line is nothing but it is a phase boundary between your one primary phase, which is alpha, and between your two solid solutions. So you have a solid solution of alpha plus beta. So it is just gives you an idea how much soluble your phase is. For example, how much soluble your B atoms are in your alpha phase. So the Solver's line just gives you that indication that if you are, for example, at 10% silver, so you will have a solubility of around, say, for example, maximum solubility that you can have it is around 8 percentage of silver. So you should always be in a lower feed if you have want a solubility of silver in your copper matrix.
Definitely.
Okay. So we will move to next question. So the next question says during equilibrium cooling, solute gets enough time to redistribute in a phase, true or false. So you have to answer this. You are doing a equilibrium cooling and you are allowing the solutes to redistribute. So is it true or false?
It is true, ma'am.
It is true, right? Because it is equilibrium cooling, you are giving it enough time for the atoms to diffuse from their positions to the positions desired because of the diffusion gradient, and it will try to achieve equilibrium once the diffusion gradient is uh, overcome. So you will have a complete homogenized phase. So that is true. Then we have another question that says if the temperature gradient is greater than the critical gradient, then the solid liquid interface will be cellular, dendritic, planar, or not sufficient information is provided. So, what could be the answer for this?
I think the answer should be dendritic.
For dendritic, when is the dendritic formed?
Then this condition of temperature gradient more than critical gradient.
Uh, no, actually, when you are having a temperature gradient that is like this, for example, your temperature gradient is like this. This is your temperature gradient when you for a liquid temperature, because you have a liquid temperature. So we can say we have a liquid temperature, and then we have a distance from some interface, right? Distance from the interface will be like this. So this is your, may we can say this is your actual temperature, And if you have a certain degree of undercooling because of certain regions, because of the interface having different compositional variations, then your this is your actual temperature gradient, this is your observed temperature gradient for a liquid when you have some compositional difference in the or non-equilibrium cooling. So you will have a higher temperature, or you need to be having a higher gradient for that. So actually in this question the temperature gradient is greater than the critical gradient, then the solid liquid interface will be actually planar, right? The right answer is it should be planar, then only you will have a solid liquid interface
Madam, that is
having a
not,
higher critical, like the gradient of the temperature will be higher.
uh, sorry ma'am, that part is not covered in the video lecture, ma'am.
You're not audible.
Ma'am, this theory is not covered in the video lecture by the respected sir, ma'am. From where we can find the theory behind these topics, ma'am.
You're not audible.
Madam, am I audible to you now?
Yes, yes.
Madam, in this question where you have said that planar is the answer. Madam, this type of theory is not a part of the week 4 lecture we have studied, ma'am. From where we can read
Yeah,
this?
I'm not able to. Can you write your whatever you are saying, because I'm not able to hear you. Maybe we can come back to you for that. Till then, we can move to the next question. Uh, there is a case where you have been discussed about, say for example, how your the what is this interface? This interface will be transferred with respect to your solidification. So if you are initially like a certain solid that is created like this, you have a solid interface, you have a solid liquid interface, then you are being told that after you are having a change in your temperature, your interface moves like this, right? Your solute concentration from the liquid will decrease and your solid interface will try to increase into the liquid interface. There is a movement of this interface from left to right. And during this transformation, there is also simultaneously a gradient difference in your temperature that says that if you have a for example, you are drawn a phase diagram where you have T1, T2, T3 temperatures, where T1 is just the initial temperature from the melt, T2 is the interface where you have solid and liquid together, and T3 is when you have complete solid solution. So at once you are just at the edge of your solid solution, which is this, like this. So this was your T1, this point is your T2, and then you have something here point where it is getting transformed, it is at T3. So you have a gradient as you move from liquid to solid. So if you are having a equilibrium type of a transformation, your temperature gradient will be based on your temperature difference, that is T1 minus T3. This is your T1 at the liquid interface, which is some function of your diffusion coefficient and your velocity. So based on this is your concentration gradient that is given. So if you have a critical gradient which is higher, than your given temperature, then you will have a non-equilibrium cooling because of supercooling. But if it is lower, then you will have a equilibrium cooling. So that is what is said, that if the temperature is greater than the critical gradient, then you have a planar. But if it is otherwise, then you will have a dendritic because you will have supercooling in the system. So this is in your covered in your lecture. You can refer to your case 3 of like cooling methods where we have solute being rejected from the liquid.
Okay, thank you.
Okay.
One more question is there.
Yes.
If the temperature gradient is below the critical gradient, then what type of microstructure we have at the solid liquid interface? Will
It
it be
will be
dendritic?
dendritic. It will be non-equilibrium cooling. So your structure will have a non-equilibrium cooling. Whenever there is a non-equilibrium cooling, then there will be dendrites formed.
Thank you.
Okay. So then we have another question that says, which of the following invariant reactions occur in the iron carbon system? Eutectic, peritectoid, monotectoid, or peritectic. So you have to say which of the reactions are possible in your uh, iron carbon diagram.
And the answer would be A and D.
You are saying D and
A.
A. Okay. So yes, you have a eutectic because you know in your iron carbon diagram you have a very important region which is used in all heat treatment methods. Majority of the heat treatments are actually concerned with this region where you have gamma region that is getting converted to your alpha and beta. So that is one, that is eutectoid region. That is not eutectic, but that is eutectoid region where we have a transformation of our gamma phase into two phases, which is alpha and cementite, which is Fe3C, right? And that is a eutectoid region. And there is another which is known as eutectic point. This is your eutectic because this is gamma getting converted to alpha plus cyanide beta. Then I have one region here which is the liquid getting transformed to alpha plus gamma plus like cementite. So that is my another region, that is eutectic. So and the third region is at the top, which is the peritectic region, where we have, first I'll write the eutectic. This is liquid getting converted to gamma plus hematite, sorry, cementite. And I have one more reaction that is known as peritectic, where we have a transformation from two, I think one solid plus liquid, which is delta plus liquid, that is giving me solid, which is gamma. So I have these three equations of invariant point because there are three phases involved. So it will have these three. So we have a correct option is eutectic, peritectic. These two are not in the iron carbon diagram. Okay. So we have eutectoid, we have eutectic, we have peritectic. Okay. Then after that we have whatever be the composition of a eutectic binary alloy, there will always be some eutectic mixture under non-equilibrium cooling. Is it true or false? We are talking about non-equilibrium cooling, and we are talking about a eutectic mixture. It says that whatever you have the composition, there is always possibility of having a eutectic mixture. Is it true or false?
Ma'am, I could not get the question exactly.
Okay. So So actually, whenever you are talking about, for example, a eutectic binary alloy, where we have something like this, when we have a, sorry, we have a region of mushy zone, which is a combination of two regions. So for example, we have a liquid, and when we have this mixture of solid plus liquid. So for example, at any point of composition, because it is saying whatever be the composition, so at any point of composition, which say for example C naught, we are saying in a eutectic binary alloy, there will always be some eutectic mixture under non-equilibrium cooling. Why? Because whenever you are at a non-equilibrium cooling, you for example you are at composition C naught. So you have two fractions of that are solidifying. One is alpha, so you have concentration of your alpha, which is your solid, okay, and you have concentration or composition of your liquid, which is Cl. At this point, when you are having a liquid composition, you will see under such region that composition of your liquid region will always be greater than the composition of your solid region, right? Because you're under a non-equilibrium condition, the rate at which you're not giving a sufficient amount for your solid to solidify, and as a result you have faster cooling rates. Your solid gets solidified while more amount of solute is being rejected into the liquid, right? So your liquid will always have more amount of solute particles when you are under a non-equilibrium condition as compared to your equilibrium condition, just because you are having a faster heating rates, right? So the solute will always have a lower concentration of your solvent solute, right? So what happens actually under this condition, you will always have a tendency for the eutectic mixture to decompose into primary alpha, which we are always saying, because we have some liquid that can dissociate into primary alpha during this faster solidifications, and once it reaches longer times or during the final transition, the liquid can dissociate into the eutectic mixture, which is the alpha plus beta. So because of faster heating rates, there occurs one difference in the non-equilibrium cooling, that you have a compositional gradient in your mixture. Once your mixture is being solidified, for example you have a bar that is being solidified, it will have compositional gradient. So for example it will have C1 because it has quickly transformed, and then it has another region that has composition of C2, which is different from C1, because you did not allow the mixture to get diffused correctly, and you did not allow the homogenization of the mixture. As a result, there is always a compositional gradient in the system. That compositional gradient results in the formation of supercooling in the structure, and that supercooling results in the formation of your primary alpha in the eutectic mixture, irrespective of whatever the composition will be. Even if you are at the eutectic point, there will always be some primary alpha because of the faster heating rates that has been formed, and the eutectic mixture because of supercooling. This is also the reason why in your alloys you have a dendritic structure. So in your pure metals, when you want to get a dendritic structure, you have to go for thermal undercooling. You have to make sure that you undercool the material or the melt then to form your dendritic structure. But in case of your alloying elements, you do not need to undercool it, because your alloying elements or your impurities create conditions in the system such a way that you have a difference in your concentration, and that difference in concentration creates a gradient in the structure, and that gradient results in the formation of two phase, primary alpha or primary eutectic phase, and your eutectic phase. So this is also responsible for your supercooling, and this is also later on helping you in the formation of dendritic structure. So in this case, whenever you have a eutectic mixture at a non-equilibrium condition, you should consider that there will be some primary alpha always formed, primary alpha or primary eutectic phase formed, irrespective of the composition. This is because there occurs a concentration gradient in your mixture. Is it clear? There is a natural undercooling in such systems. Is it clear?
Ma'am, I have a question in this
Yes.
problem. Ma'am, when we say binary alloy and if we say
Uh,
eutectic binary alloy,
in
so
eutectic binary alloys,
what is mean by exactly mean by eutectic binary alloy versus binary alloy?
binary alloy is just there are two components that are
Yeah,
mixed together, copper
yeah,
nickel. So
yeah,
this
yeah,
is a binary alloy. But if you have,
yeah.
say, for example, when you're talking about blast furnace or slags or in pyrometallurgical processes, say, for example, you have three phases. You have calcium, silicon, iron. So you have three phases. So that is a ternary diagram. The three phases interact with one another to form certain phases. So that is a ternary diagram. But when you have a binary, then you have only two components interacting, copper and nickel, for example. You don't have any third phase, and you can form eutectic points. Even in when you have a ternary diagrams, you treat the ternary diagrams as you take two components at a time. Say, for example, A, B, C are the three components. So if you take A and B, there could be some eutectic formations between the A and B, so you can study that eutectic. Then there could be some eutectic between B and C also, so you can study that, but that will be eutectic in a ternary alloy. There will be a ternary phase.
Ma'am, my question is that what, when we say we have a binary alloy, I got the answer. There are two components. But when we say eutectic binary alloy, so ma'am, as I have studied through the lectures, binary eutectic can be shown by a single point on the phase diagram. So what exactly mean by eutectic alloy? That was my question.
Well, you are not clearly audible, but what I understand is that eutectic is just a point. It is an invariant point in a phase diagram where there will be three phases in equilibrium, and those three phases in equilibrium will result in the formation of eutectic point. Eutectic point is nothing but it is a point where you have a melting of the alloy which is much lower than their pure components, which is a copper tin alloy, for example. Copper and tin have a high melting point individually, but when you form, or a lead tin alloy, for example, when you form a solder, you will have a eutectic point that forms an alloy, and that eutectic point you can have a meltdown. You have a complete conversion of your liquid into two phases, copper alpha, lead alpha and tin alpha. So that will be your eutectic point, but you have a binary. Just means there are two components.
Yes, ma'am. Thank you, ma'am.
Okay. So then we have another question that says coring is a phenomena related to equilibrium cooling, non-equilibrium cooling, inhomogeneous solute distribution, or casting.
Non-equilibrium cooling.
Non-equilibrium cooling. Okay, and anything else? Actually,
Casting.
happens in the
Cast,
regions where you have a difference in your temperature, right? Because if you're cooling, the cooling is not at a same rate, or the phases that are being solidified are not not solidified at a same rate. So for example, if you have, for this mostly happens when you have a two phases, which is, say, for example, A, and you have some B which has a very low melting point. The melting point difference between the two is very large between A and B. And once this happens, once you try to solidify the mixture, there could be a possibility that your, because there are two phases, alpha and beta, there could be possibility because your B phase, which is at a lower melting point, it starts to solidify it before actually your alpha is being solidified. So your core, which is the center of your melt, will form B atoms, right? But as the time progresses, then we have a solidification of alpha also, right? With along with B. So we can have alpha plus beta. But the core was concentrated with your beta atoms, which was the beta phase. So this could be because of the high difference between your melting points of A and B, and it would result in an inhomogeneous solute distribution because you will have some nucleation sites for the low melting point phase to occur, and then B atom will solidify first, then the A element or A atoms. So this will result in inhomogenized solute distribution. So that is also possible. Coring is also related to non-equilibrium cooling. It is also related because there will be a gradient, temperature gradient difference when you have an inhomogeneous cellular distribution. And this can also happen in your castings, because normally when you go for castings, when you put your melt in a molten, in a say mold, this mold is always at a lower temperature because it is at room temperature, while your melt is at a very high temperature. So this mold will have different heating losses along the wall, along the center. So this also results in the formation of coring because there is a thermal gradient in the system involved, and that is why in such casting processes you get a dendritic type of a structure, or you get coring possible. So anything that will result in your temperature gradient that will allow one of the phases to solidify first will cause coring in the structure. So it could be because of non-equilibrium cooling, it could be because of the inhomogeneous cellular distribution, and it could also be because of casting. Okay.
Ma'am,
So
could it be related to solidification also?
what coring is related to solidification? Yes. Yes, coring is related to solidification. It is just a phenomenon how your liquid melt or your mixture of phases is being solidified. It is related to solidification only.
Okay.
Okay, so we have another question that says the crystal structure of austenite in iron carbon system is FCC, HCP, BCC, or simple cubic. You should remember these, that what are the phases of in our iron carbon system. Majorly there are like the one that are mainly concerned for the iron, we have alpha, which is ferrite, then we have gamma, and then we have delta. These are the three major phases. Mostly we are concerned with alpha and gamma in your heat treatment or in your steel applications. So alpha is your ferrite phase, so this is your BCC. So whenever you are given a steel, consider, and it is at a room temperature, the structure will be BCC, right? The gamma phase, if you are at equilibrium cooling, if you are doing equilibrium cooling of a structure, and then gamma is another phase, so that is your austenite. So austenite is always FCC, and your delta is also actually BCC. So you should remember what kind of a crystal structure you are having, because this will help you in later on doing various heat treatments, or playing with the atoms or alloying elements in the structure. So the right answer is FCC. Okay. Also, somebody had asked a question related to HCP packing crystals that I think I will also cover here. Uh, there was a question related to how the planes of HCP are arranged. What is the stacking arrangement? Say, for example, you have a hexagonal cell. This is your hexagonal unit cell. It's not very good. Okay. This is your hexagonal unit cell. So in the top, which is the plane for the hexagon, you have six atoms. This is the hexagon plane for your HCP. You are having six atoms. And if you have seen closely a hexagonal unit cell, there are atoms at the center also. There are three atoms. One is at the center, and there are two atoms at the back, making such triangular type of arrangement of atoms. These are actually the arrangement of atoms, because when you see arrangement of atoms in a 3D lattice, say for example, you will you are actually seeing this magnified view of the atoms which are arranged like this, right? Something, this arrangement of atoms. Okay, you are just seeing a magnified view of that in this HCP here. So you have planar hexagon which is having six atoms, and then you also have a plane at the bottom which is having six atoms, right? So you can say that your plane at the top and the plane at the bottom have the similar arrangement of atoms. It is the same. The stacking is same. So this stacking of atoms can be referred to as A stacking. And because we have a different arrangement of atoms stacked at the center, so we have B, and then we have this which was similar to A, right? because this is one unit cell. So there will be many more unit cells after this, before this. So the overall stacking of your hexagon will always be AB, AB type. So this will be a sequence of atoms that will be arranged. So AB, AB, AB will be the atom arrangement of the atoms in your hexagonal unit cell. So this will give you an idea that how atoms are arranged. If they are arranged in a similar fashion, then you can name it by same label. And once the arrangement changes, you can change the label. Okay. This was
Yes,
asked by
ma'am.
something,
Yes, ma'am.
someone.
Thank you, ma'am.
Okay. Okay, so now we have another question. It says that you have a solid which is getting converted into two solids on solidification, because this is a phase diagram. These are all solidification reactions. So, what kind of a reaction is it? It is peritectic, eutectoid, eutectic, or peritectoid? We are actually having, when you have a normal system of a liquid getting converted to two solids, which is alpha plus beta, the famous reaction. So this is actually the eutectic reaction. But when you are having a transformation to from a solid, the you always change it to toid, eutectoid, right? So solid 2 gives you alpha plus beta. So this is your eutectoid reaction. One solid gives you two solids. Because they are different solids, so we name one solid giving 2 and 3 solid. So the reaction is eutectic, not eutectoid, right? Not eutectic, because eutectic is from a liquid, while as eutectoid is from a solid. So this is a general question that you should remember. What is the percentage of carbon in iron at peritectic point? So you know what is a peritectic point in your iron carbon diagram? It is a point here at the top. If you have seen it somewhere like this, so you have a peritectic point somewhere here, and then you have a gamma phase below it. So you have a peritectic point here where we have a liquid plus delta giving you two phases, two solids, which is delta plus gamma, right? So the point at which this peritectic point occurs is at what carbon percentage? Because this is very important to know when you have concerning with the solubility. Anybody can remember that? We have a reaction here for delta plus liquid that is giving us directly gamma, right? I think I have not drawn it very right, so it will be something like here. So the liquid plus delta will be giving me the gamma, just as you had for a austenite phase. You know that for austenite phase the maximum solubility that it can achieve is at 0.76. This is something we all know, that is gamma. This is your 0.76 percentage of carbon. For this, for a delta phase, it is actually at a point of 0.18. So what does this mean? This means that at 0.18 percentage of carbon, the peritectic point is possible only when you have a percentage of carbon around 0.18 in your say for example in your steel. In your steel, when you have a percentage of 0.18, then only you can think of formation, that is a maximum percentage to form a peritectic point, to form a transformation from liquid plus delta phase of iron to your gamma phase. So you should remember these points, like what is the maximum solubility a ferrite can have, solvus line, the solidus line, the maximum solubility of your gamma phase. So that is 0.76. Similarly, you should remember the maximum cementite percentage that we are talking about. So that is around 6.6 percentage. So based on your iron carbon diagram, you should remember the various temperatures and the various points at which the carbon percentage is forming invariant points. So then we have another structure which says microstructure of hypoeutectoid steels. At room temperature contains ferrite and pearlite, laterite and pearlite, cementite phase and pearlite, alternate layers of ferrite and cementite phases. I want you to answer this.
Right and perlite.
Okay, so right, we have two phases. One is ferrite. Ferrite is nothing but your alpha phase, which is your primary alpha, if you can say, and your pearlite is a mixture of your alpha and beta phase, which is alpha plus beta. So pearlite is a laminar structure of your alpha and beta phase. Okay, then we have another question that says gamma iron occurs in the temperature range of 912 to 1400, or 912 to 1400 Fahrenheit, 1400 to 1539 degrees Celsius, 1400 to 1539 degrees Celsius.
And the correct answer is C.
1400 to no, we are talking about gamma iron. We are not talking about delta iron. The gamma iron is stable from this region, 912 to
Right.
1400.
A.
A, right. Uh, so A is the right option. Now we have question on the lever rule again. So I want you to attempt this question and try to see what is the answer for this. So we are given a binary system A and B. As you were saying, what was the binary system? We have two components A and B. A solid of 70% A, which means 30% B, because it is always 100%, coexist with a liquid of 20% A, 80% B. The overall composition is 38%. The fraction of solid is. So you have to calculate what is the fraction of solid, weight fraction of solids actually. So weight fraction of your solids. So I can say it is actually solid is here A, so weight fraction of A we can say. So I want you to attempt this question and try to answer. Because the all of the river rule diagrams, if you have a phase diagram, it is very easy to calculate it. But here you have to form the phase diagram first and then calculate it. So I want you to make a phase diagram and then calculate. After that, I will also solve it. So you can take 2 minutes and solve it. So we have any answers by now?
and these values 70% and 20% of A, will it be P of
Like what?
and
Which is the right option from A, B, C, D? I'm not. You're not audible. Which is the right option? So okay, we try
and,
to solve it because
and am I audible?
yes.
And I want to first clarify from you that these value of 70%, 20%, will it be, are they belonging to the value we call PF and PL?
You're not audible still. You can write it, and then we can see. You can write it till then. I'll try to solve it. So if we here we have to construct the phase diagram here. So we have a system A and B. So just going by one terms where we have A here and B here. Just okay. And then we are saying it is having a solid of 70% A coexist with a liquid of 20% A. So just because we have two binary diagrams, we know it will form a isomorph like this. So we have a overall composition is 38%. Okay, and we have this composition here, and then we have also, because we are at a certain composition of a binary alloy, and then we have 2 points which says it is a solid, because this is a liquid, this is just solid, so it is having a solid of 70% A. Okay, so right, because we are trying to draw a diagram in terms of B as an alloy in A, right? B is a percentage of in A. So this is 70% A and 30% B. So we will write it in terms of B because B is a solute in A in our diagram. What we are trying to draw here. So this will be 30 RB. Then we have it coexists with the liquid of 20% A, which is 80% B. So this is our 80%. So we have 30 and 80 fixed in the diagram, and it says the overall composition is 38%. So okay, so assuming this is 38%, this is actually the 38 percentage of A, right? Because the question gives you about the concentration of A only, and then there is a extra information of B. The overall composition is 38%. This is A, right? But because in this diagram I'm drawing a percentage of B in A, so I can write for B as it is 100 minus 38. I can do it in this way. So that will be around, I think, 62, right? So this composition is my 62 here. This is one way to do it. There is also one way that we do take this 38 directly. Both ways the answer should be same because the sum of the two phases is always 100. So I can take it like this. I can take B. I can take A. I can take again the isomorph for this. Okay, this is my liquid, this is my solid. Now this point here, it will be 38 if I take it directly. Then I have a composition of solids and liquid given. The composition of solid now will be 70. Okay, okay, so we can draw it this way.
Here it will be 20%.
We can draw it this way, right? I'll try to draw it a little clear. The main thing that in your phase diagram is always how you draw the diagram. Once you are done with drawing the diagram, then you can easily calculate anything. But it is the problem, from the problem you have to draw the diagram, that is important. So now we can say this is our 70% A, this is our with a 20% of A, right? Now you can easily calculate your fraction of alpha from either of the two diagrams. So you can calculate what is the fraction of alpha. Tell me what is the answer. You just need to know in what position you are, whether you are making a B as a solvent, or you are making, sorry, solute, or A as a solute. Based on that, you can draw the diagrams, but always the data will be given because the percentage of your phases will always be 100. So you have to calculate the weight percentage of your alpha.
And 0.36.
What is 0.36?
0.36.
Right, this is your right answer. So you should be aware when you are given a questions like this how to construct a phase diagram, and from the phase diagram how to get your percentages. Okay.
And I have a doubt in this question
Mm-hmm.
that how would you select that which one is solvent and which is the solute? Like you have
Yeah, you
drawn
can
two
do either
diagrams.
of the way because I have drawn it both ways. I have drawn it both ways that if B is your solvent, then you can draw this way. You just see they just flipped the diagram. The diagram just got flipped. So
Yes, 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 yes.
you have a B, A as a solute in B. So you can read your phase diagrams both way. Whenever you any phase diagram that you are given for iron, carbon, for silver, copper, copper, nickel, any diagram, you can read it if it is a alloy of nickel in your copper or copper in your nickel. Both ways you can write that. Just reading your scale, because if you have, this is simple, if you have a scale which is having A and you have B, this is always that A here is actually 0 and it is going to a scale of 100. Sorry, B is actually 0 at this point and it is going to a scale of 100. And
Yes,
what,
ma'am.
what is the value of A here? For
And
A, it is
B,
0
here
here
it will be 0.
and it is going to 100
Yes,
here. So just the scales of the A and B are important. Okay.
yes, ma'am.
Okay, so we can move to next question. The question says consider a binary iron carbon alloy system at its eutectoid temperature of 727. So we have iron carbon. We know that eutectoid temperature, which is 727, we have a conversion of our gamma iron to our two phase system, which is alpha plus beta, right? We know it is a eutectoid. So you should take every word from your question as some information. So this is gamma going to give you alpha plus beta. So you have a eutectoid temperature 727. So you are given that the carbon composition of the alloy is 0.60. Now you should know this eutectoid temperature which we are talking about, which is gamma, giving me alpha plus beta, right? In a phase diagram, I have a temperature that is given, it is 727. I should know what is this composition, maximum composition, which is the eutectoid point. So this is actually, I think it is not given in the question, right? So first we see what is given. It is given in a carbon of composition 0.6 is given. Your composition of ferrite is given. Your composition of perlite is given. It is not actually perlite. It is cementite. Composition of your, okay, yeah, perlite is given, but I think it should not have been written like this. So you can see this is composition of your perlite, which is 0.76 percentage carbon. Using the lever rule, calculate the fractions of ferrite and perlite phases present in the microstructure at this temperature. So you should understand that at what temperature you are actually. Are you in the hypoeutectoid or you are in the hypereutectoid? So for that, you should know what is this point. This is your eutectic point. So you know uh, for this transformation of a eutectoid, this is actually 0.76 percentage of carbon, right? So the composition of an alloy is given zero point 0.6. So you are in the hypoeutectoid region, right? You are below this gamma region. So you are in this region, which is nothing but alpha plus gamma, right? So you are somewhere in this region, which is 0 0.6. So this is your region, right? Now you are to calculate the fraction of ferrite and perlite phases present in the microstructure at this temperature. So you are at the eutectic temperature. You don't have to calculate alpha and primary alpha or eutectic alpha. You just have to calculate your uh, eutectic mixture. Okay. So can you try to attempt this question and then tell me the answer?
Ma'am, I have tried this
You
question.
have to make a lever.
The
You have
fraction
two
of perlite comes
phases.
out to be 0.783.
What are the two phases? This is my alpha phase. This is my alpha plus gamma phase. This is gamma phase. So this is my eutectic point 0.76. This is my maximum solubility of alpha from the Solvers line. This is also given because you are given a composition of ferrite. This is 0. You are already given in this question because it is at a eutectoid point. So this is 0.022, right? So nothing else, you just have everything. So you have to calculate 0.002 is your one phase, and then other end of your lever is 0.76, and then you are somewhere here which is 0.6 of your alloy. So you can calculate your alpha, which is ferrite, and perlite. So what is the weight fraction of your alpha, which is perlite, and what is the weight fraction of your actually liquid? We are actually sorry, not liquid but gamma phase. So we are calculating the weight fraction of our gamma phase, which is nothing but actually the weight fraction of your perlite, because that will be dissociated into at the eutectic point into alpha and beta phase. So you can write it as a weight fraction of your eutectic or perlite. So you have to calculate these two weight fractions. And please tell me what will be the answer.
Uh, am I audible, ma'am?
Yes.
Ma'am, I have got ferrite as 0.22 and perlite as 0.78.
How we decided?
I am using the lever rule, ma'am.
Uh-huh. Not audible. What you want to ask? Like using the river rule?
I got the answer.
Mm-hmm.
Ferrite comes out to be 0.22 and perlite comes out to be 0.78.
Okay, okay. So you have ferrite as 0.22 you are saying, and perlite you have 0.778.
78. 78.
Okay. Yeah, that is fine. So always in this, because you are in a hypoeutectic region, your perlite will always be more and your ferrite will always be less, right? Because it's a mixture, small ferrite and large perlite. So I think that is also done because in these questions, because this was in a eutectoid temperature already given, so you had also given the conditions for your alpha ferrite composition of perlite, so it was easy. But if it is not given and it is at another temperature, then in case of iron carbon diagram, you should at least remember the points of carbon. You should know what is the eutectic percentage of carbon, eutectoid percentage of carbon, eutectic percentage of carbon, to calculate such numericals. Now we have another question that says, how is the maximum solubility of carbon in iron 6.67 in iron and carbon phase diagram calculated? So you know, whenever you have a phase diagram for iron carbide, which is actually the iron and iron like iron and iron carbide diagram. So it is not an iron carbon diagram, but it is an iron carbide diagram, right? So you have read the diagram up to your X scale. If you have closely seen, it is up to 6.67, where you have a then coming a beta phase, like here you have a beta phase coming from this point. So it is a maximum is actually 6.67. So you are given an iron carbon phase diagram up to 6.67 percentage only. Why is it so? So you can take a 1 minute to think on it. Why we are given the maximum percentage of carbon in iron based on iron carbon diagram as 6.67 only? Why not more than that? You know what is this Fe3C? This is your cementite phase, right? So, because you are having a diagram between your iron and cementite phase, this is your iron and this is your cementite, this is Fe3C. So, how do you calculate this maximum solubility of carbon? First, we will see what is this cementite phase. Can you say what is the percentage of carbon in the cementite? Right? We can say that. We can say that based on what is the percentage of carbon, because we know one carbon is actually 12 grams. Percentage is nothing. Concentration of that species divided by the total concentration. Carbon is 12 grams. The whole cementite is 12 grams plus the weight of your iron, right? This will give you weight percentage of carbon in cementite. So you have 56 multiplied by 3. So what is the value here that you are coming? This is actually the weight percentage of carbon in cementite. What is the value that is coming here?
Six point 6.67%.
Right. So that is the reason why you have the iron cementite diagram, iron carbon diagram up to 6.67 only, because the maximum percentage of carbon that can exist in a cementite phase is only 6.67, right? So that is why we have phase diagrams up to 6.67 only for iron carbide diagram, right? Because that is the maximum solubility of carbon in iron, maximum percentage of carbon in cementite actually. Okay, so now we have another question. Okay, so we will do this question, which is the mass fraction of total ferrite and total cementite in an iron carbon alloy are 0.88 and 0.12 respectively. Is this a hypoeutectoid or a hypereutectoid alloy? Why? So can you try to solve this?
And is it hypereutectoid alloy?
It is hypereutectoid. It is hypereutectoid, but how have you calculated it? Have you decided to that it is a hypereutectoid?
Not because cementite uh, only exists in hypereutectoid alloy, not in hypo.
Uh, okay. It is actually, when you are talking about total cementite and total ferrite, these are nothing but these are actually your alpha plus beta phases, right? Alpha and beta phases. This is not about cementite because you are still going to have alpha and beta, right? Uh, in your hypoeutectoid alloy, you have a mixture of your eutectic mixture, which is alpha and alpha plus beta. You have alpha and alpha plus beta. While in your hypereutectoid, you have alpha plus beta. Sorry, you have alpha plus beta and beta, which is cementite. Right? Here you are not given that it is only a cementite and a eutectic mixture to decide on the basis of like statement. One way to do is that you are given two values. So you understand that the total ferrite value is large. That is only possible because first we'll try to draw it a diagram. Gamma giving me alpha plus beta, right? So you are given mass fractions of your alloys. So you are given actually weight fraction of your alpha, which is 0.88, and you are also given weight fraction of your beta, which is 0.17. So if you are in this region, because you are alpha plus beta region, you always apply a lever rule, right? So you have two species here and here. Just based on the value of your alpha and beta, you can decide whether weight fraction of your alpha and beta, you can decide whether it is a hyper or hypo. The weight fraction of alpha will be is greater than your weight fraction of beta. So this is only possible when you have a larger fraction of lever rule, that you have a fulcrum that is towards left side, right? Something like this. Then only you can have a larger portion of alpha that will be divided by the total lever rule, total lever length. So that is one reason. That is only possible when you have a hypereutectoid. Now, if you do not want to go into that details, we will just go and calculate the value of our concentration or composition, because we know this is our 0.76. Less than that is your hypo, higher than that is your hyper. So you should be aware that your eutectic point is 0.76. So what we try to do, we try to solve these alpha and beta. So we will try to solve it. How will we solve it? Because we know the first, let's go like this rule. We'll try to form a lever again. So you have to find something point where we have a composition, that is to be, that is something that we have to find. We are given endpoints, that is 6.67 and 0.02, 0.002, right? Because this is a maximum cementite, this is for a maximum ferrite, and we are somewhere in between that in a phase diagram of iron carbon diagram, right? So weight of alpha, we can calculate it. Say for example, this is our y, this is our, because we have to only calculate, say for example, alpha we do. So I will write it as y divided by 6.67 minus 0.002. So you can calculate what is the value of y. What is the value of y here?
Point 88.
Pardon, please.
And will it be point
What is the
zero two
value
or
of your
point double
y?
zero two?
I have to calculate what is the point of this composition. This is composition C naught. I have to calculate the value of your y will be equal to
Between 4 and 5.
5.86 will be your value of your y, right? Then what is actually y? Y is nothing but it is 6.67 minus your C naught is equal to 5.86, right? So you can calculate the value of your C naught. It is around 0.8. Okay. So if it is 0.8, it is greater than 0.76. So it is a hypereutectoid. Is it clear?
And the correct answer is hypo or hyper.
Hyper.
Yes, ma'am.
Right. So because it has a greater than 0.8 concentration, so greater than 0.76, so it is a hypereutectoid. So you have to find the value of your concentration that will help you to determine whether it is hypo or hyper, and you should know the points of your invariant points in the diagram. Okay. So I think that is all for today. So if you have any questions.
Ma'am, I have some objection in the assignment number 3 for
Mm-hmm.
which Q has been published.
Mm-hmm.
So would you please see the few of the questions?
What was the question?
Ma'am, the same question you have taken in the last problem solving session,
Mm-hmm.
but the answer which has been given in the Q
Mm-hmm.
is different from what you have said in the last Sunday.
Okay, so what
So
was the question?
yeah, I'll speak out the question, ma'am.
Mm-hmm.
Ma'am, in this question, you have to find that what is the name of the defect when there is a mismatch between one grain to another grain.
Mm-hmm.
If you remember the question, ma'am.
Mm-hmm.
So you said the answer is only uh, uh, grain boundaries.
Okay.
But what the solution has been provided by the NPTEL team, it includes both grain as well as grain boundaries. So
Okay.
would you clarify that which answer is correct?
Well, twin, it is twin depends. If it is a twin inside a grain, then you cannot say it as a like you cannot call it to be this mismatch between the crystal orientation. But if your twin is present as a crystal orientation defect, like because of your twins your crystal orientation is being affected, then you can call it to be a like it is a both ways it is right. So I think it will be a more of a like it is just a out of box question that has been given. In cases of twin boundary, if it is changing the crystal orientation or if it is a crystal orientation defect, then when you are talking about orientations and twin is one of the defects there, then you can say it is a this mismatch between the grains. But if it is present inside the grains, the twins are present inside the grains, then you cannot say it is a mismatch between the two grains. So it depends how your twin will behave. So you can answer as grain boundary, you can answer as both of them. But generally, if you take all cases including, then it should be both. But if you go in like specifically, then either grain boundary is also right.
And actually, the question has this type of
So
language.
it depends how the twin will behave.
Yeah. Mismatch of orientation
You're not
from one
audible.
grain to adjacent grain. And I have posted the question in the chat box. Would you access it, please?
You're not audible.
Ma'am, I have posted the question in the chat box.
You have wrote the question in the
Chat box.
okay.